One thing everyone can experience is that when you go further down in a body of water like a swimming pool or a lake, the pressure increases with depth. This feeling you experience is the effect of hydrostatic pressure. Hydrostatic pressure is the pressure in a liquid at a given depth. This is due to the force of the gravitational pull acting on the liquid. This force occurs regardless whether or not the liquid is at a standstill or in motion. Due to the molecular makeup of liquids, this force acts both downward and outward as well as between the molecules of the liquid. It is this force that forces liquid to an area of least resistance. For example, water out of a hole of a paper cup or a leak in a pipe for a gas. Increase in elevation of a fluid increases the amount of hydrostatic pressure. Fluid flowing downward gains increased pressure as well. Temperature is another factor that affects pressure because when temperature increases, molecules move at a faster rate, increasing the pressure.
To demonstrate hydrostatic pressure, we have set up a little demo. Here we have a bottle of water with two holes at different heights. When we unplug the holes, pay attention to the distance that the water flows out from the bottle. After the demonstration, we will explain the mathematical equation that defines hydrostatic pressure and how it verifies the results seen in the demo.
Okay. Observe the distance the water shoots out from the bottle.
Okay, what did we notice about the distance of water flow from the bottle? We saw that the top holes flow went only a little distance from the bottle, while the bottom hole went a further distance than the top hole. This can be explained from analyzing the equation for hydrostatic pressure. Now let's take a look at the equation for hydrostatic pressure and how it's derived. A good place to start is to remember what our definition of pressure actually is. Pressure is equal to the amount of force divided by the cross-sectional area that the force acts upon. Let's look at our demo of the 2-liter bottle, and looking at the two holes in the diagram, we will assign the holes 0.1 and 0.2. We know that the pressure at 0.2 is going to be greater than the pressure at 0.1 by a given amount.
You experience that in the most basic application of going into a swimming pool, you feel more pressure or force pushing down on you. The reason for that is that at the bottom of the pool, there is extra weight of water on you. Looking at the diagram, we will assign the height of the water h. Now we assume the holes are plugged so there's no flow, so we can assume the net force acting on that volume of water is equal to 0. Now the volume of water is equal to the cross-sectional area times the height of the liquid. The net force is acting on the water is the water pushing from below exerting an upward pressure we'll call F2. We also have a downward force, F1, from the water pushing down. And lastly, there's a force of gravity acting as well at the center point, equal to mass times gravity. So the sum of the forces are equal to 0. We know that F2 was upward, making it positive. F1 was downward, making it negative. And F of G, which is mass times gravity, downward, making it negative. Now, we know before that pressure was equal to force divided by a cross-sectional area, which can be rewritten as force is equal to pressure times the cross-sectional area. Now we can take this and plug it into our net force equation. So F2 will become P2 times area, and F1 will become P1 times area. And that leaves us left with mass times gravity. So looking at mass, we knew that density is equal to mass divided by volume. So rewritten, it's mass is equal to density times volume. We know volume is cross-sectional area times the height. So mass will then become density times area times height. Now this can be plugged into our net force equation. So it'll be density times area times height, also times the gravity. Now looking at our equation, we have A in every component on the one side of the equation. That can be divided out to cancel out your areas. Now we will take the density times H times G and add that to the other side. So our equation will become density times gravity times height is equal to P2 minus P1, which is the change in pressure. Bringing up our hydrostatic or static pressure equation, change in P is equal to density times gravity times height.
So we now understand that the pressure at hole 2 is greater than the pressure at hole 1 based on how further you are down the liquid, and also by the density of the liquid and the gravity acting on the liquid.